Hello students, welcome to our today's lesson. Today with this video we shall start the chapter number 5, that means magnetism and matter. And in this video I shall discuss these topics from chapter 5. So first we have to know what is magnet, then the bar magnet, the magnetic field lines, magnetic dipole moment of an atom due to revolving electron, and the last one, magnetic field due to magnetic dipole or bar magnet. So let's start our discussion. So what is magnet? A naturally occurring ore of iron, magnetite attracts small pieces of iron towards it. The phenomenon of attraction of small bits of iron, steel, cobalt, nickel, etc. towards the ore is called magnetism. A magnet is a material or object that produces a magnetic field. The magnetic field is invisible but is responsible for most notable property of magnet. So magnets are of two types. One is natural magnets and the other one is artificial magnets. Next, the bar magnet. The bar magnet has two poles similar to the positive and negative charges of an electric dipole. One pole is designated as north pole and the other as south pole. When a bar magnet is suspended freely, these poles point approximately towards the geographic north and south poles respectively. Like magnetic poles repel each other and unlike magnetic poles attract each other. I repeat, like magnetic poles repel each other and unlike magnetic poles attract each other. If a bar magnet is dropped into a pile of iron filling, the maximum amount of filling get deposited near the ends of the magnet and almost nil in the middle. The pattern of iron filling deposits as poles suggests that attraction is maximum at the two ends of the bar magnet. These ends are called poles of the magnet. The poles of a magnet can never be separated. Okay, so from this figure you have the idea about the bar magnet. Next, the magnetic field lines. The magnetic field lines are a visual and intuitive realization of the magnetic field. The magnetic field lines in a magnetic field are those imaginary lines which continuously represent the direction of the magnetic field. The tangent drawn at any point on magnetic field lines shows the direction of magnetic field at that point. Their properties are as given below. The magnetic field lines of a magnet or a solenoid form continuous closed loops. This is unlike the electric dipole, where these field lines begin from a positive charge and end on the negative charge or escape to infinity. The tangent to the field lines at a given point represents the direction of the net magnetic field B at that point. The larger the number of field lines, crossing per unit area, the stronger is the magnitude of the magnetic field B. The magnetic field lines do not intersect, for if they did, the direction of the magnetic field would not be unique at the point of intersection. Okay. Next is magnetic dipole. Magnetic dipole. So, a magnetic dipole is an arrangement of two magnetic poles of equal and opposite strength separated by a small distance. So, suppose we have S pole and N pole. We have S and N, then separated S and N pole separated by a distance. Suppose distance between them is twice L. Okay, so that is a bar magnet, a compass needle, etc. are magnetic dipoles. The two poles of a magnetic dipole or a magnet called north pole and south pole. So this S for south pole and N for north pole. Okay, are always of equal strength and of opposite nature. Further, such two magnetic poles always exist in pair. Now, what is the magnetic length of magnet? Magnetic length of a magnet is defined as the distance between two poles of a bar magnet. So, I am writing here magnetic length of a magnet is defined as the distance between two poles, of a bar magnet it is a vector from S pole of the magnet to its N pole and is represented by twice L. Okay. Now magnetic dipole moment. What is magnetic dipole moment? We have to know magnetic dipole moment now. Magnetic dipole moment. So magnetic dipole moment is the product of the strength of either pole and the magnetic length of the magnet. It is represented by capital M, and the direction of magnetic dipole moment is same as that of twice L. Therefore, we can write M is equals to M into twice L. So, here direction for M, and this is one M, this is another M. What is small m? Strength of the pole. See, strength of S pole is also M and strength of N pole also M. So strength is same for the two poles. That means for S pole and for North pole. For South pole and North pole, the magnetic strength is M and the distance between them is twice L. So capital M, that means magnetic dipole moment, is the multiplication of strength and the distance, M into 2L. So its SI unit of M is ampere meter square. Ampere, AM, meter square. SI unit of magnetic dipole moment. So this is important for 1 mark, like what is the SI unit for magnetic dipole moment, or what is the unit for magnetic dipole moment. So SI unit of magnetic dipole moment is ampere meter square. Okay. Now our 5th topic, magnetic dipole moment of an atom due to revolving electron. Magnetic dipole moment of a revolving electron. Okay, so to understand this problem we have to draw one diagram. Suppose we have one path, circular path, through which electron will move. So at the center charge is ZE. Suppose electron is moving this direction, E minus, charge of electron is minus, and the radius of this circular path is R, and the mass is M. Okay, so this simple picture of an electron of charge minus E revolving around a nucleus of charge plus ZE in an atom. So an electron moving in such a circular orbit is equivalent to an electric current. So whenever one electron is in motion, that means current is generated. So this electron motion is equivalent to one electric current, and the current I is equals to E divided by T. What is T? T is the time taken by the electron to complete the circuit of its orbit, or to complete this circular path. Clear? Now, if R is the radius of the orbital for the electron and V its orbital speed, suppose V is the velocity or speed for electron, then what we can write? Suppose give this equation number 1. So if B is the velocity and the T is the time, then T time taken is 2 pi R by V. Why 2 pi R? Because perimeter of this circular path is 2 pi R. So T is equals to, we can write 2 pi R by V. So give this equation number 2. Now from 1 and 2, what we can write? If we put the value of T in equation 1, then we can write I is equals to E divided by 2 pi R by V. So here we can write V. So I is equals to EV by 2 pi R. Give this equation number 3. Okay. The magnetic moment arising from the orbital motion of the electron is, we know M is equals to I into pi R square. I into pi R square. So this implies, in place of I, if we put this value, so EV by 2 pi R into pi R square. Okay, so 1 R cancel out, then we get EVR by 2 pi. M is equals to EVR by, okay, pi also cancel out, so EVR by 2. Give this equation number 4. And the direction of this magnetic moment is perpendicular and into the plane of the paper. If M is the mass of the electron, so we can give here, we can write capital M also to represent the mass of electron, because two symbols is same. This is magnetic moment, this is mass. So we can define them with two notation, capital M or small m. Okay. So if m is the mass of the electron, the revolving electron also possesses an angular momentum with magnitude L is equals to mvr. Okay. Now this Vr, in place of Vr, we can put L by M from this equation. So from this equation we can write Vr is equals to L divided by capital M, and we can put the Vr value here. So M is equals to E, Vr means L by M, and we have 1, 2. So EL by twice M, and vectorically we can write M vector is equals to minus E by twice M into L. The negative sign indicates that the two vectors M and L are in opposite direction. This M vector and L vector are in opposite direction. That's why we using here one negative symbol. Clear? Okay, now move on our last topic, magnetic field due to magnetic dipole or bar magnet. Magnetic field due to magnetic dipole or bar magnet. Okay, suppose we are going to find out at an axial point. At an axial point. So we have to draw one diagram. This is our S pole, this is N pole, and one axial point. The point on this axis is axial point. Suppose one point is P here, and the force directed along S pole is S, and for N pole is Fn. Okay, and the distance between these two poles is twice L, and the middle point here, and from this middle point the distance of the point P is R. Okay, this is our figure. So we consider a bar magnet of pole strength Qm and length twice L. Suppose pole strength Qm and length twice L, as shown in this figure. The axial point P at a distance R from the center of the bar magnet. So this is the center. Suppose this is O, center of the bar magnet, and the distance between the center point and the P is R. So the force exerted by N pole, we can write Fn is equals to mu naught by 4 pi Qm divided by R minus L square. So we are using here the previous chapter's concept from electricity. And in the same way we can write Fs is equals to mu naught by 4 pi Qm divided by R plus L square. Now strength of the magnetic field at P produced by the magnet, then B is equals to Fn minus Fs. Sorry, this one Fs. So Fn minus Fs. So we have to subtract Fs from this, and we can take mu naught by 4 pi and this qm common, right? So mu naught by 4 pi into qm common, then 1 by r minus l square minus 1 by r plus l square. Okay, if we solve this equation and if we simplify, then we get mu naught by 4 pi twice mr divided by r square minus l square whole square, where this m is equals to twice L and Qm. Okay, the magnitude of magnetic dipole moment. So for a short bar magnet, when L is far less than R, then we can neglect this L term, L square term. Okay, so then we get R to the power 4 and R cancel out. So mu naught by 4 pi 2m divided by R cube for a short bar magnet. Okay, so that's all for today's class. Thank you so much for watching the video.